Hi everyone, welcome back. This is our second to last lecture, so congratulations on making it this far. If you're watching this in order, this is the Monday of the last week. So we do have our final at the end of the week. Um, so let's jump into it. So as you see, this is section 5.3. We're talking about the fundamental theorem of calculus. So this is a very, very important idea in calculus. Um, I've mentioned the past couple of lectures and kind of hinted at the fact that we're going to find a way to take an integral, a definite integral using the antiderivative rules that we learned in 4.10. This is when we're going to do that. So the fundamental theorem of calculus has two parts, as we'll see. One of the parts is more of like a trick. It's saying if you have this one specific case, if you're looking at this one specific thing, there's a really easy way of solving it so that you don't have to go through the 10 to 15 steps it'll take to actually do it out explicitly. Now, you can do it out explicitly and you'll get the same answer. It'll just take you longer to get there. So that's going to be part one. Part one is kind of the trick. Part two is the more straightforward way of doing it, where it's saying this is how you actually take the integral using bounds, and we can plug in the bounds and get the answer without having to use geometric formulas or endpoint approximation or anything like that. So this is a very important lecture to understand, especially like I said, if you're going into Calc 2, this is going to be a very, very important idea throughout the entire course. All right, so let's go ahead and first take a look at something that should seem familiar. So what we're going to look at is the mean value theorem for integrals. So that says f of c equals 1 over b minus a times the integral from a to b of f of x dx, where f of x is continuous over a to b, and there's some point c in a to b. Now you may look at that and think, huh, that looks kind of familiar. This right here looks a little familiar. And if it looks a little familiar, that's because it is. So this formula, if you recall from the last lecture, is what we called uh, av. This was the average integral when we were computing the value. So this is just another way of looking at it. Now we have an official name. We have the mean value theorem for integrals. And if you looked at the one theorem from the last lecture where it was like lowercase m times b minus a equals or less than or equal to the integral less than or equal to capital M times b minus a, and you were a little bit confused why that was. This is why that is, because they're talking about an average integral here. And so what they're saying is that you can also state it as f of c times b minus a. So essentially what we did in that specific inequality there was we multiplied the b minus a to both sides of our inequality. So that's really all it was. Again, that's not something that I expect you to memorize. All right, so this is very important. So this is the fundamental theorem of calculus part one. In this course, I don't expect you to memorize which is part one and which is part two. But if you do go into a further calculus course, you may be expected to remember that this here is part one. And when we get to part two, that is going to be explicitly part two. All right. So again, this is very, very important. If f of x is continuous and capital F, we remember, is the antiderivative, is defined as capital F of x is the integral from a to x of f of t dt. This is important. Then capital F prime of x equals f of x over a to b. So this is what the first part of the fundamental theorem of calculus tells us. So if you have some a value, which is going to be like the lower part of your boundaries, if you have some a value going to a variable, it could be any variable. It doesn't have to be x. It could be x cubed. It could be 12x squared for all I care. Of some function that will be in a different variable than the variable you have as your bound. So here it'll be t. Typically, we will use t. Then you take the derivative of this. It's saying you can get rid of this right here and just plug in x or whatever variable into your function. Now, it's not quite as cut and dry when you do have something other than just an x. If it was a 2x or a 12x squared, it's not quite as cut and dry as take your variable and plug it into your function and get rid of everything else. There's one extra step. But this is the general idea of it. So something to note, though, the lower bound must be a constant and the upper bound must be a variable. So there might be a question that they're trying to trick you with where it's the integral from x to a, and they say take the derivative of this. And they are expecting you to use the first part of the fundamental theorem of calculus, but the trick is that they want you to try to plug it in from there. If you have the integral from x to a, what you have to do is you have to negate it and use that one property of integrals, negate the integral and flip the bound so that the boundary with the variable is going to be on the top and the boundary with the number is going to be on the bottom. If it's anything other than just a single x or a single variable, plug that into t, or again, any variable that's in your integrand here, plug that thing into t, then multiply your function by the derivative of that bound. Okay, so let me show you what I mean by that. This is like kind of the chain rule for the fundamental theorem of calculus part 1. What this says, if you have the derivative of your integral, so that's what this was saying, right? It's saying this is capital F your integral, so the derivative of your integral, where u of x is now some function of x that's not just x. You have a still on the bottom. This is the proper setup for the fundamental theorem of calculus part 1. Then this is equal to taking your function and plugging in u of x, which is what the fundamental theorem of calculus part 1 says, is take your variable, plug it in, whatever that thing is, you plug it in everywhere you see a variable, in t in this case, in your function. But then you have to multiply the entire function by the derivative of your bound. All right, we're going to do some examples, but this is very important to note because, again, something else they'll try to do to trick you on really anything at all is going to be give you an upper bound that is something other than just an x, and they expect you to make a mistake, which is going to be maybe not multiplying by the derivative of that upper bound. And that's a great place for you to kind of show your understanding and be like, no, I do understand that this is going to be an applied chain rule for the fundamental theorem of calculus part 1. And it's a really easy way to get points if you were to ever have this on any sort of an exam in my class or in a future class. Okay, so let's go ahead and take a look at an example. So this one is a pretty simple example, pretty straightforward. We see g of x is the integral from 1 to x of 1 over t cubed plus 1 dt. And we're looking to use the fundamental theorem of calculus part 1 to find the derivative of this thing. So something that I want to note is it has to be the derivative of. So don't make the mistake of thinking that for any integral with a lower bound of a number and an upper bound of a variable, you can just plug it in, because that's not at all the case. It is only the case when you take the derivative of your integral. Okay, that's what the fundamental theorem of calculus part 1 says. Derive your integral, then you can do this thing. And that says you can just take your upper bound, whatever your variable is, and plug it into your function. So this says that g prime of x is going to be equal to 1 over, we'll plug in x into your t cubed, so x cubed plus 1. Your derivative of x is just 1, so we don't have to multiply by that. So this is your derivative function. This is, like I said, the trick to doing this, because theoretically you could determine this integral, explicitly compute it, and then find the derivative, and you would get the same answer. But this is a single step with very little thinking involved, whereas that would be a very long and large problem with a lot of thinking involved. All right, now let's do an example that's slightly more complicated. So given that capital F of x is the integral from 1 to the square root of x of sine of t dt, find the derivative. Again, it has to be the derivative. You cannot just say that the integral is plugging in the values, because that's not true. All right. So what this says, this is going to be the applied chain rule. This says you can just plug in that value. First of all, just plug it in. Don't touch it. Don't do anything with it. Plug it in. After you plug it in, multiply the entire thing by the derivative of whatever that bound is. So this says that f prime of x equals, well, here it's sine of t. So that's sine of, well, your t becomes your upper bound. So this is a square root of x. This is fine. But now we need to multiply by the derivative of our square root of x. So I'm going to pull that off to the side. Derivative of the square root of x. We know we can't take the derivative of a square root. So this is the same thing as the derivative of x to the 1/2 using the power over root rule. And now using just the general power rule, we can say this is 1/2 x to the negative 1/2. So this is going to be the applied chain rule that we're multiplying by, 1/2 x to the minus 1/2. And this is your derivative of that function. Again, this is so much faster than actually trying to find the integral, because the integral is not too bad, right? The integral of sine we know is going to be negative cosine. We don't yet know how to compute using proper bounds, but when we would plug in the bounds using the fundamental theorem of calculus part 2, We can do that, and then we can take the derivative of that, and we would find that we do get this as an answer. But again, this is just really long. So you can verify your answer using that method, but typically it would be okay to just say like, hey, I'm using the fundamental theorem of calculus part 1. Here's my answer. All right. This is the last example of the fundamental theorem of calculus part 1. So what you notice is that f of x is the integral from x to 2x of t cubed dt, and we're looking to find the derivative of that. So what you should first think, what should immediately jump out to you, is that you have two variables, and you are trying to use the fundamental theorem of calculus. So we know that in order to use the fundamental theorem of calculus part 1, it has to be the integral from a to whatever variable you have of your f of t dt, where your number is on the bottom and your variable is on the top. Here we have an issue. Our issue is that we have a variable in both spots. So this is where we have to know our tricks and rules for how an integral works, our properties for how an integral works. So before we do any type of calculus, well, I guess it is still calculus. Before we do any type of derivation, should I say, what we want to do is we want to split this integral up to kind of resemble this. So we're going to need to make two integrals. So what we do, remember, like I mentioned, there may be some times that you do want to split an integral up into two parts. This is going to be one of those times. So f of x equals, I want to have some integral of t cubed dt with some sort of bounds, and then I want to add that to some other integral of t cubed dt, and I want to figure out what my bounds are going to be. Well, we know that in order to add integrals, we need the same number kind of across from each other. So either bottom top or top bottom. And it really doesn't necessarily matter what order we put them in. I usually do the lower one first and the upper one next, just because it makes more sense in my head to do it like that. So I know I need x on my lower bound, and I need 2x on my upper bound. And I need those on two different integrals because I can't have two variables as my bounds in order to use the fundamental theorem of calculus part 1. Well, now we know that we need two numbers here and here that are going to be the same number. And in fact, we had a rule that said if you had the integral from a to b of f of x dx, you could actually write this as the integral from a to c f of x dx plus the integral from c to b f of x dx. And that's kind of how you would like combine your c values, right? There's some overlap with the c. So if you're saying, well, look at this chunk and this chunk, but those chunks connect, well, then you're actually just looking at this chunk. That's essentially what it's saying. So we just need to choose a number here. And it really does not matter at all what your number is, because as you saw with our fundamental theorem of calculus, they just put a to be any number at all. So choose your favorite number, whatever number. I'll choose 0 because 0 is just a good number to use. So now we have two different integrals that each have a single number as a bound and a single variable as a bound. But this has the variable as a lower bound and the number as the upper bound. And we know that's an issue. We know that we have a problem with that. So the first thing that we have to do is we need to change this to fit the proper form of the fundamental theorem of calculus. So we're going to say this is equal to, and we know the rule that says I can change this to be 0 to x if I negate my integral. And then I can keep everything else the same. This one we don't have to change because this is already of the proper form. So integral from 0 to 2x of t cubed dt. And now we can apply the fundamental theorem of calculus twice. We can apply it to this one and we can apply it to this one. So when we apply it to this one, we're going to bring the negative down for the ride. And then this just says take your variable and plug it in. So this is x cubed. And since we're just x, the derivative of x is 1, so we don't have to multiply by that. So this equals negative x cubed plus, and now we can go ahead and apply the fundamental theorem of calculus to this one. So it says take this and plug it in. So that's 2x cubed. So be very careful if you have something other than a single variable, you are plugging that entire thing in for t. So that is 2x quantity cubed. But because this is something other than just plain old x, we do have to multiply by the derivative of that thing. So the derivative of that thing is just 2. So I might simplify this a little bit, write it in like a standard form. 2 cubed is going to be 2 times 2 is 4 times 2 is 8 times another 2 is 16, x cubed, and then minus x cubed. And would you look at that, we have the same exact base. And so we can write this as 15x cubed. And this is going to be your solution for this problem. This is your f prime of x right here. And this is also f prime of x. Whereas this is still your f of x because all we've done is change the bounds. So this is the derivative of this specific function. All right, now we can take a look at the fundamental theorem of calculus part 2. So this is the evaluation theorem. This is what I was talking about earlier with how we can actually plug bounds in. So what this says is if f is continuous and f capital is the antiderivative, same thing that we always have. And then the integral from a to b of f of x dx is capital F of b. So that is the antiderivative of f plugging in at b minus the antiderivative of f plugging in at a. This is very important. So what this says, essentially, if you can find the antiderivative of the integrand, then you can evaluate that derivative by evaluating the antiderivative at the endpoints of the interval and subtracting. And in fact, to be a little more specific, subtract the upper bound plugged in minus the lower bound plugged in. And be very careful when you're plugging in the lower bound if you have multiple terms in your function that you put parentheses, because you need to subtract the entire thing, not just the first term. So make sure you're always using parentheses unless you just are integrating a single term, then it doesn't necessarily matter. It doesn't hurt, but it doesn't matter. So this is the fundamental theorem of calculus part 2. Let's go ahead and let's look at this. When we use antiderivatives and look at indefinite integrals, we always put plus c. So when we did integral f of x dx, we said that this was capital F of x plus c. And what you notice in this last one here is that we didn't have a plus c term, right? And the only time we didn't have a plus c term in 4.10 when we were talking about antiderivatives was when we had initial conditions. And essentially the initial conditions relate very closely to when we have bounds, right? So that's telling us something about the function. And so this is actually going to be kind of helping us determine exactly what our function is going to be. So the bounds are an exact value. Because we're determining a number, we're not going to need a plus c term. And that's exactly what this is saying. So we will always have our quote unquote c be 0 when we're evaluating a definite integral, because we're just going to get a number out when we solve it usually. All right, now let's go ahead and take a look at an example. This is what I wanted to get to. So before, when we were solving things like this, what we did was we used geometric formulas. So we would say, oh, this looks like a trapezoid, a triangle, anything like that. And we would use the area formula and evaluate that, maybe a rectangle. This, however, t squared minus 4, we know that's a parabola. Well, that's not a nice geometric figure. So now we actually can use our antiderivative techniques to find the antiderivative of this, and then use the fundamental theorem of calculus part 2 to evaluate this to find the exact area, as opposed to when we computed the Riemann sum using the left and right endpoint approximation, we found an approximate area. This will give us an exact area. So what we're going to do is we are going to compute the antiderivative first, and then we'll plug in the bounds after. So I'm going to say that this is equal to, first, let's do the antiderivative. What we remember about computing antiderivatives of just regular old like power functions here, it's up a power, divide by that power. All right, so let's go ahead and do this example. So again, we always want to put our variable, put a fraction. Up a power from 2 is 3, and then we divide by 3. Minus, anytime you just have a constant, it's the same thing as saying t to the 0. And so this is also the same thing as just kind of putting a t onto it. So this is the same thing as 4t. Over 1 if you want. Dividing by 1 is the same thing as just saying 4t. And we don't have to put c, again, because we're now evaluating for a number. So this is where things change a little bit. So this is where, pay attention to my notation. So I'm going to put parentheses around this. We need to denote now that there's still bounds, because here, this is saying from -2 to 2. But when we're just looking at this doesn't tell me where I'm evaluating. So we use this concept of an evaluation bar when we were talking about evaluating derivatives, specifically when we were looking at like implicit differentiation. We used an evaluation bar. So that's a single bar down, except now instead of just writing at the bottom here exactly what we're evaluating, we're going to continue to use the same vague notation of the lower bound on the bottom and the upper bound on the top. So we're going to say -2 to 2. And this is saying evaluate as -2 on your lower bound and 2 on your upper bound. And what we remember from the Fundamental Theorem of Calculus Part 2 is that it says we take f of b and we subtract f of a, where this capital F denotes the antiderivative that we just took. So step 1, take the antiderivative. Step 2, plug in your values, upper bound first, subtract, plug in your lower bound. So let's do that. So this is 2 cubed over 3 minus 4 times 2. This is plugging in your upper bound. Subtract, big parenthesis again, because we're subtracting a quantity. Plug in your lower bound. This is -2 cubed over 3 minus 4 times -2. And I know earlier I did say don't simplify your answers. And that came to derivatives that had like ugly answers. For this, you do want to simplify to get a number because this is just going to be a single quantity. So this is 2 to the 3 is 8. This is 8 over 3. Minus 4 times 2 is -8. Minus, this is -2 cubed. -2, an odd power is negative. So this is -8 over 3. Minus is plus 8. We can continue to simplify this. So we have minus a negative. So this is 8/3 plus 8/3, which is 16/3. -8 minus 8 is -16. We can adjust this as well. Maybe put this over 3, multiply this by 3. And this gives us 16 over 3 minus 48 over 3, I believe. I'll double check. Yep. And what this gives us is going to be a -32 over 3 for our answer. So as you see, we wind up with a number, and this is the exact area of this curve from specifically -2 to 2. All right, so definitely be aware of this notation here. This is going to stay consistent when you're taking any calculus course, and this is what I'm going to be using for the duration of the course for today and, well, today and tomorrow, I guess. All right, let's do another example. So evaluate using the Fundamental Theorem of Calculus, Part 2. So what we again notice when we look at something like this is that we cannot just take the antiderivative because we know that the integral sign doesn't distribute over division. So what we have to do first is we have to create separate terms of addition and subtraction. And because this is divided by a single term, we can in fact take each term in the numerator and divide it individually by what's in the denominator. Recall that the square root of x is the same thing as x to the 1/2. So what that's telling us is the integral from 1 to 9 of x minus 1 over the square root of x dx is the same thing as the integral from 1 to 9 of take our first term and divide it by this. So I'll say x to the 1/2 minus our second term over x to the 1/2. I'll put big parentheses indicating that we are taking the antiderivative of that entire thing with respect to x. And now I'm going to simplify. Still have not taken any integral, so I have to continue to write our integral, very similar to when we were doing limits, and we had to continue to write the limit until we actually took the limit. So x minus 1/2, so this is 1 or 2 over 2 minus 1/2, which is the same thing as 1/2, minus this right here. All we have to do is negate the exponent and bring it into the numerator. This is x to the minus 1/2 dx. And now that we have a term and another term separated by subtraction, no fractions, no funny business going on, we can use the power rule that said up a power, divide by that power. So up a power is 1 over 2 plus 1, which is the same thing as plus 2 over 2, which is 3 over 2. So this is x, remember fraction bar, so x to the 3/2 divided by 3/2 minus, we need -1/2 plus 1, which is the same as 2 over 2, which is just going to give us 1/2. Fraction bar x to the 1/2 over 1/2. And then again, it's this entire quantity evaluated from 1 to 9. I might simplify this because if you remember, we don't like dividing by a fraction. So what we're going to do is we're going to keep, change, flip. So this is the same thing as saying 2/3 x to the 3/2 minus 2, because 2 over 1 is just 2, x to the 1/2 evaluated from 1 to 9. And now we can actually compute that. This might be a little bit easier to actually convert back into a root, because again, since we're not allowed to use a calculator, we can convert this to a root and it becomes a little bit easier to deal with. So if we, again, maybe don't evaluate and we convert to a root, this is power over root. So this is 2/3 times the square root of x cubed minus 2, then x to the 1/2 is just the square root of x, evaluated from 1 to 9. And now we can plug in, and it probably makes a little bit more sense. So this is plug in the upper bound. So this is 2/3 times the square root of 9 cubed minus 2 times the square root of 9. And then we want to subtract. What happens when we plug in the lower bound? Well, let's plug it in. Quantity, 2/3 times the square root of 1 cubed minus 2 times the square root of 1. Let's simplify this. First of all, I'm going to pull this off to the side. We can simplify this by hand. So instead of actually doing all the math, we have that the square root of 9 cubed is the same thing as the square root of 3 squared cubed. And if we reversed those, that's 3 cubed squared. And this helps us because we know when you have a square and a square root, they cancel out. So this and this goes away, which tells us that it's the same thing as saying 3 cubed, which is 27. So you don't need a calculator to compute this. We can just use basic kind of algebraic manipulation. So this is 2/3 times 27 minus 2 times the square root of 9. Well, the square root of 9 is 3 times 2 is 6. So then this is minus the square root of 1 cubed. This looks like 13. This is 1 cubed is obviously 1. So this is minus 2/3. Minus 2 times the square root of 1 is 2. And now I'm going to spare you the common denominators and everything like that and tell you that the answer is 40/3. And if you were to go ahead and that you would be expected to make common denominators and simplify, you would in fact get 40/3. All right, this is the last one for today, and then we'll have one more lecture, and then you have a final, and we're done. Also a written assessment. I forget exactly. That one was already due, I believe. The third written assessment would already been due. So you only have the last homework and your final exam to do after this. So let's go ahead and compute this last question. So what we're looking at is the integral from 1 to 2 of x to the minus 4 dx. As we can see, the bounds are lower to upper, which is fine. X to the minus 4 is fine. We can use the power rule for that. So this one actually is pretty simple. This one's easier than the other one we just did. So the integral of x to the minus 4, we can put an x, put a fraction bar, up a power. The only thing is that we have to make sure when we're going up a power, we're not being more negative. So that was with the derivative, we're subtracting 1. Here we're adding 1, so negatives become more positive. So -4 plus 1 becomes -3. Divide by -3. But then there's no other terms. So this is evaluated from 1 to 2. Now, this is something that you would probably want to adjust before you plugged in these values because you probably don't know what 2 to the -3 is. I don't. So let's adjust this before we plug in our bounds. First of all, I'm going to pull out this -1/3. And then this right here says if we negate our exponent, we can bring this whole term to the denominator. So this is x to the 3 down here. So what we get is -1/3x cubed. Quantity evaluated from 1 to 2. Now we can go ahead and plug in the upper bound. And so what we get is -1/3 times 2 cubed minus quantity negative. And this is where we have to be very careful about our negatives because we are subtracting a negative. 1/3 times 1 cubed. So let's see here. 2 cubed is 8. 3 times 8 is 24. So this is -1/24. Minus a negative is plus. 1 cubed is obviously 1. This is just 1/3. If we adjusted this a little bit, we can move this 3. We could turn the 3, multiply that by 8 times 8. So this is negative 1/24 plus 8/24. And what we get is 8 minus 1, which is 7/24. And that is our answer. All right. So this is the end for today's lecture. This is what I've been kind of hinting at since we started antiderivatives. This is the way to evaluate derivatives, the easiest way to evaluate derivatives. Tomorrow, we will talk about what happens when we can't just do a very straightforward either power rule or maybe know like the integral of sine is negative cosine. If we can't very easily take the antiderivative, as I mentioned, there are several tricks to doing that. We only cover one in this class, and that's what we're going to be covering tomorrow. That'll be called substitution. So as always, if you have any questions, please reach out to me, and I will see you for our last lecture tomorrow.